Okay, so today we're going to start Chapter 9 on infinite series. Okay. And the last chapter we talked about sequences. So sequences were just a bunch of numbers, usually separated by a comma, that followed a specific formula. So when we look at today, we're going to look at a series. That's the sum of the terms of a sequence. So finite sequences and series have defined first and last terms, whereas infinite sequences and series continue indefinitely. So here's an example and how we would write infinite series. So we express that. So here's a sub 1 plus a sub 2 plus a sub 3 plus a sub n. And you'll notice there's always going to be a dot, dot, dot kind of before and after because it does not have a finite number of terms. So we express that with the sigma notation from k equals 1 to infinity. And actually k can start from any value. So k can start with a 1, it can start with a 0, it can start with a 3. Okay, and these just represent the number term of the series. So let's just practice. Again, some of this will be a little bit of review from pre-calculus, which I know it's been a while, but just writing out the first four terms of each series. So the sum from n equals 1 to infinity of 1 over n. So this is, again, we think of the n equals 1, that's our counter. So it starts out with 1 over 1, which is 1. Then we go to n equals 2, so it just counts. So that's going to be 1 over 2. Next one, n is 3, so 1 over 3. And finally, n is 4, so 1 over 4. And that's all we need to do. We don't actually have to add it. Next one. Now you'll notice we're starting here at n equals 0. And so whenever we have a negative 1 to the n, basically that means it's going to be an alternating series. It's going to alternate between positive and negative. Where it begins depends on what n is equal to. Since n is equal to 0, it's going to be 1 over 2. Then when n equals 1, it's going to be minus 1 over 2. Then when n equals 2, it's going to be plus 1/2. When n equals 3, it's minus 1/2. Next one. So this is not alternating. It's just going to be positive terms. So when k equals 1, we have 1 over 2. When k equals 2, we basically have 2 times 3 on the denominator, so that's 1/6. When k equals 3, we get 3 times 4 on the denominator, so that's 1/12. And finally, we have 1 over 4 times 5, so 1/20. The next one, we want to work backwards. So given the series, we want to come up with what is the expression for the nth term, a sub n. So basically what you want to look for is a pattern, or what are we doing? Well, the numerator is staying 1. But the denominator, we think of, well, this is 2, 4, 8, 16. These are all powers of 2. The first one is a 2 to the 0, 2 to the first, 2 squared, 2 cubed, 2 to the 4th, and so on. So we want to be able to write a sub n. You can write it as 1 over 2 to the nth power, or you can write a sub n as 1 over 2 all to the nth power. It's the same because the 1 in the numerator. So either one of these would be fine. Okay, the next one. So we see that first of all, it's an alternating series, so we know we're going to have a negative to an nth power. And these look like 3. This one's 3. And this one's 3 times 10. Then this is 3 times 10 squared, 3 times 10 to the 3rd. So a couple of different ways we can write this. One way is we have this 3, and then it's times 10, or actually I'm going to put in a negative 10 to the nth power. And then we just want to make sure when n equals 0, do we get 3? When n equals 1, do we get minus 30, and so on. You could also have separated that negative 1 to the power out of there, but since I know it's multiplied by 10, we can include that negative. Okay, partial sums, which is basically what we are looking at in example 1 and 2. These are partial sums. This would be the 4th if we were to look at the first four terms added together. But the idea with partial sums is we're looking for also, is it going to converge to one particular number? So basically we look at the sum, we start with the first term, the sum of the first two terms, the sum of the first three terms, all the way to the nth term. So if this partial sum has a limit, which is what I was just saying, so if this partial sum has a limit s as n goes to infinity, we say that it converges to the sum. Otherwise, we say the series diverges. So otherwise, it diverges. So let's take a look at example 3. Compute the limit of the partial sums to determine whether the series converges or diverges. And you may actually just by looking at some of these be, kind of see what's going on. So here, if we look at s sub 1, well, that's just 2, right? That's the first term. Then s sub 2 is going to be 2 minus 2. That gives us 0. S of 3, so that's going to be 2 minus 2 plus 2, which is 2. S of 4 is going to be 2 minus 2 plus 2 minus 2, which is 0. So just by looking at the sums, it's just flip-flopping between 2 and 0, 2 and 0. So this is not converging to one limit. So therefore, this sum diverges. Okay, let's take a look at the next one. So s sub 1, now we have it written as 7/10, so I'm actually just going to write it like that. S sub 2 is going to be 0.7 plus 0.07, which is 0.77. S sub 3 is going to be 0.7 plus 0.07 plus 0.007, which is 0.777. S sub 4 is going to be 0.7 plus 0.07 plus 0.007 plus 0.0007. And so what do you notice about these? So we end up with a value where it's 0.7 basically repeating. And so since this has a limit, and so this is going to have a limit, and 0.7 repeating is actually equivalent to 7/9. So therefore converges to the limit of 7/9. Okay, so if we have an infinite series and it converges, then we know the kth term has to be equal to 0. So again, if we know this converges, then the kth term, as k goes to infinity, that has to be equal to 0. If the kth term does not equal 0, then the series must diverge. Okay, so again, if we look at, the above part B, if we were to look at this, we really have 7/10 to the nth. That's going to go to 0, so we can see that that's going to converge. Now, that series in example 3b is what we call a geometric series. Okay. Each term is obtained by the preceding term by multiplying the same number r. In this case, r is 1/10. So a geometric series is, again, when you have what's called a common ratio. So your common ratio is equal to r. A, this is what we consider our first term. And one of the things you may remember from pre-calculus, if the common ratio, if the absolute value of that common ratio is less than 1, then we have the sum. This is something that we need to remember. The sum is equal to a over 1 minus r. And if that's the case, then we know it converges. If the common ratio is greater than or equal to 1, then it's going to diverge, because think it's going to be increasing without bound. That's how we know it's going to diverge. And then we have what's this is something called the interval of convergence. And that comes directly from this part where the absolute value of r is less than 1. So that interval of convergence is always going to be, the common ratio has to be greater than -1 and less than 1. So let's take a look at a number of these geometric series. We want to determine whether the series converges or diverges. If it converges, give it sum. So really all we want to look at here, we want to look at what the common ratio would be. And just a reminder, the common ratio is basically any two terms where you take the ratio, you could take the ratio of the second term divided by the first term, and that's going to give us the common ratio. Or anytime you have a sub n over a sub n minus 1, that will give us the common ratio. You need to have two in a row. So here, if we look at, here's a sub 2, and here is a sub 1. So the common ratio is going to be 12 over 36, which is equal to 1/3. And that's going to be less than 1. Therefore, we know it converges. Now, if we know that, then we can find the sum. The sum is going to be, so A is referring to the first term, so it's going to be 36 over 1 minus 1/3. So we have 36 over 2/3, which is going to give us 54. So there's our sum. Okay, part B. So now this one is written in summation notation. If you want, if it's difficult for you to see, what the parts are, you can actually just write out some of the series. So this is going to be 4 plus 1 plus 1/4 plus 1/16, and so on. Or you can just see this is to a power of n minus 1. So our common ratio is actually just going to be 1/4. So that is less than 1. Therefore, we know it converges. And we can find the sum. So our sum is going to be, now the first term is going to be when n equals 1. So that's going to give us 4 over 1 minus 1/4. So we have 4 over 3/4, which is 16/3. Okay, next one. This one we can see here, just by the 5/2 to the nth power, we can see r is 5/2. This is greater than 1, therefore this diverges, and we do not need to do any further work. Because basically the sum will go to infinity. Okay. Next one, here, if we want to just compare -0.2 over 2, this is actually going to give us a -0.1 for the common ratio, which is less than, or that absolute value is less than 1. So we know it's going to be converging. You can also identify r as right here because that's to the nth power. Again, just a different way to see this written. So since this converges, we have a, which is 2 over 1 minus -0.1. So that's going to give us 20/11. Okay, and part E. So we look at the common ratio. Well, pi squared over 4 over pi over 2 actually ends up giving us pi over 2. Pi is bigger than 2, so that's bigger than 1. Therefore, this diverges. Okay, so next we have a series where we want to find the interval of convergence and the function of x represented by the geometric series. So previously, we actually had the numbers. We didn't have any variables for x, okay? We had all the numbers that were involved. And now what we're saying is, okay, now we're going to introduce this variable x. We want to basically create a geometric series. Okay, so we want the series to be geometric and we want it to converge for r, the absolute value of r less than 1. Okay. So here, this piece, this is our r. So this is going to converge when the absolute value, the absolute value of x plus 1 is less than 1. So we have that. So we have -2 to 1. So our interval of convergence is -2 to 1. And then the sum of the series, okay, so we know from previously this is going to be the first term. So if you look at the first term in this series, so when n equals 0, we get 1 over 1 minus or actually, I'm sorry, let me back up here. If we look at the first term, this is actually going to be, let me write it out here. So it's going to be 1, and then when n equals 1, we're going to get a minus x plus 1. And then when n equals 2, it's going to be plus, and then x plus 1 squared, and then minus, and then x plus 1 to the third, and so on. So actually the radius of, not the radius, the common ratio is negative, but it doesn't really impact this inequality. We would end up with the same result. So actually when we go to find the sum of the series, we want negative and then x plus 1. So we actually get 1 over x plus 2. So the function that's going to be represented is going to be f of x equals 1 over x plus 2. And again, that's for values -2 to 0. Okay, next one. Maybe this time I'm going to just write out the first couple of terms so we can see this. So when n equals 0, we get 3. When n equals 1, we have x minus 1 over 2. When n equals 2, and so on. So our common ratio is going to be x minus 1 over 2. So this is going to converge for values where x minus 1 over 2 is greater than 1, greater than -1, and less than 1. So we're going to multiply everything by 2. We're going to add 1. So we get -1 to 3. And now we want to find the sum. So we have 3, it's the first term, 1 minus x minus 1 over 2. So we get 3 over, and then 2 minus x minus -1, so plus 1, all over 2. So we get 6 over 3 minus x. So our series is going to be represented by the function 6 over 3 minus x, and that's going to be in the interval from -1 to 3. Okay, here we have, let's see, writing out a few terms, we have when n equals 0, we get -1/3. When n equals 1, when n equals 2, so my common ratio is x plus 1. So this is going to converge for x plus 1 less than 1 and greater than -1, so -2 to 0. And then our sum is going to be -1/3, and then we have x minus x plus 1. So we have -1/3 over 1 minus x minus 1, which is going to be -1/3 times 1 over -x, so 1 over 3x. So our function is going to be 1 over 3x, and the interval is from -2 to 0. So we just had a little bit of practice doing that, representing functions by series or series by functions. And so if we talked about if the absolute value is less than 1, then we're going to have the series 1 plus x squared plus x cubed all the way to xn, and continuing is going to be equivalent to 1 over 1 minus x. So here, basically what that means geometrically is what we're saying is this geometric series is represented by this function. So we can actually look at, here they graphed 1 plus x squared, 1 plus x squared plus x cubed, 1 plus x squared plus x cubed plus x to the fourth. And when we're looking at the interval from 0 to 1, we're saying from that interval from 0 to 1, the values are converging. They're getting closer and closer. And then when x is greater than or equal to 1, the values are not even close. So basically what we want are values that are going to be the values of x that are, the absolute value of x are less than 1. Okay. Next page, we want to look at a power series. Power series, this is a series, not necessarily geometric, although geometric is a type of power series. And here's the form for that. Oops. So here's your power series. And we say the power series is centered at x equals 0 for something like this. And then if we have this x minus a, then we say the series is centered at x equals a. So again, like I said, geometric series is a specific type of power series. So this is the power series centered at x equals 0. It converges on the interval from -1 to 1, and it's centered at x equals 0. So for example 6, we want to find a power series to represent the given function and identify its interval of convergence. So basically, we want to relate this back to our sum formula. So remember the sum formula, this was equal to a over 1 minus r. So we want to just identify the different parts. So a is going to be equal to 1, and r is actually going to be equal to -3x. So our power series is going to be 1 minus 3x plus 3x squared minus 3x cubed plus 3x to the fourth, and so on. So -3x to the nth, and then it continues. So our interval of convergence is going to be the absolute value of -3x less than 1, which, think about, that's going to be -1 to 1. So we divide by -3, so that's going to be 1/3, and of course that makes everything switch. And then we want to just rearrange it. So from -1/3 to 1/3, that's our interval of convergence. So here's our power series, and that's our interval of convergence. Okay, next one. So same thing. A is equal to 3. R is equal to x cubed in this case. So our power series is going to be 3 plus 3x cubed plus 3x to the 6th plus 3x to the 9th plus, and then it's going to be 3, and then x cubed to the nth power, and so on. And our interval of convergence is going to be the absolute value of x cubed has to be less than 1. So basically, x has to be between -1 and 1.